We shall now start a discussion of the representation of signals and systems for the discrete case, discrete signals and systems and their representation. One might argue that in the real world there are no discrete signals. Now, if one takes that view, then one is simply redefining what one means by the real world. Because in today's world, with digital cameras, with digital recording of audio signals, we do have discrete time signals, and they are very much part of the real world. You might say that they are not present in the natural world, but then we will have to debate about what is natural and what is unnatural, what is artificial and what is natural. Instead, one can just confine oneself to the to a study of the advantages and problems that one associates, that one can associate with a discrete formulation of the theory of signals and systems, in contrast with the continuous formulation that we have spent some time on so far. We already have an introduction to discrete sequences, which are called discrete time signals. We have an introduction to the discrete complex exponential in considerable detail. All this has already been covered in this course. What we are now going to look at is a parallel study, a study along the lines we have already travelled, but this time for discrete time signals. There, if you recall, we started with periodic continuous time signals of the form x t equals x t minus t. So, the period was t. Now, in this case, we start with discrete sequences, which we will denote by x n equal to x n minus n. So, the period is now an integer that we call n. We also generally indicate that the independent variable of these signals is a discrete variable by using brackets instead of parentheses for n, as we have done just now. All right. Now, given this, let us try to see if there is some relationship we can draw between discrete time sequences and continuous time functions, which are both periodic. Suppose I try to construct a discrete time sequence by sampling a continuous time signal. Suppose further that x t is periodic, as has been given over here. I want to ask the question, if we have sampled a continuous time periodic signal x t using a discrete set of samples which are placed, say, t naught seconds apart from each other, under what circumstances will the discrete sequence that results be periodic as well? So, the samples we have are x, let me call this new discrete sequence as, say, y n equals x of k t naught for x t equal to x t minus t. So, capital T is the period of repetition of x t, and t naught is what we call the sampling interval. So, at integer values of k, you get k t naught points on time, and at those instants the value of x t will be taken as the values of the sequence y n. Sorry, it is not k, we will call this n. So, y n equals x of n t naught. This is what we have. Now, we want to ask, is y n periodic? Periodic. Now, it is a discrete sequence. So, its periodicity or otherwise will be judged by whether it meets the criterion for periodicity of a discrete sequence as set out in this equation. This is what is going to determine that. Now, we will see, is y n periodic? Now, there are several cases to consider. A, if t by t naught is an integer, then y n is periodic. And one period of y n will coincide with one period of x t. This is the first case. Now, going to the second case, B. If t by t naught is not an integer, but k t equals L t naught, then again y n is periodic, and one period of y n will coincide with k periods of x t. This is when we have t by t naught equals L by k, where L and k are integers. So, both for t by t naught an integer and for t by t naught a rational number, y n is periodic. The third case is when t by t naught is not even rational. When this happens, even though x t is periodic, y n will never be periodic. Y n is not periodic. So, this tells us that when you construct samples of, when you elicit samples of a periodic continuous time function, certain criteria have to be met for this sequence of samples to also be periodic. And if the sequence of samples has to have a period which coincides with the period of the original continuous time signal, certain additional criteria, namely that t by t naught must be an integer, must be satisfied, otherwise it does not happen. Right. So, with this much in hand, we will completely disassociate ourselves from continuous time signals and just deal blindly with discrete time sequences which are periodic. So, from now on we will only consider periodic discrete time sequences. Periodic discrete time sequences which satisfy x n equals x n minus n, where capital N is therefore called the period of the sequence. We want a theory of representation for periodic discrete time sequences. A theory of representation means we have to look for preserved classes. Which are as small as possible. Preserved classes which are as small as possible. We could generate a set of preserved classes on the basis of finding harmonically related periodic signals that are harmonically related to x n. So, one approach is to seek preserved classes of signals harmonically related to x n. These would give us signals which are not necessarily only complex exponentials, but because of this fact they will not have the special property in relation to linear time invariant systems that complex exponentials have. These classes would also be larger in size, because they would contain classes of periodic complex exponentials which are also harmonically related to x n. So, for reasons very similar to those that we discussed in the context of finding periodic preserved classes of complex exponentials to represent periodic continuous time signals in the context of LTI processing, linear time invariant processing, we will proceed to also look at preserved classes only of complex exponential periodic complex exponentials for the representation of periodic discrete time sequences. The reason, of course, is that a complex exponential, periodic or otherwise, preserves its form under linear time invariant processing, just as it did in the continuous time case, it does so in the discrete time case as well. So, we want to look at preserved classes of complex exponentials discrete, of course, that are harmonically related to xn. Xn has a period n. So, if any complex exponential has to be harmonically related to it, then it must satisfy the property that it also should repeat after every n members of the sequence. That is to say, if now we have a discrete complex exponential of the form e to the j 2 pi by n into n, 2 pi by n into k n is to be considered for being harmonically related to x n, then it must satisfy e to the j 2 pi by n k n must be equal to e to the j 2 pi by n k n minus n. I have already let the cat out of the bag by saying that the fundamental frequency must be 2 pi by n. If I had not told you this, and if I had simply written these equations as e to the j omega naught n, and here also if I had written just e to the j omega naught n must be equal to the this, then we would really have the job on our hands of finding out what choice of omega naught would yield this property of being periodic with respect to capital N. And it does turn out that omega naught equal to 2 pi by n does yield this feature. In order to verify this, we will see the following. Consider e to the j 2 pi k by n times n. I have not specified what k is. I will leave it just as an integer for the time being. Now, let us see what happens. Let us put n minus n over here. So, we will consider this minus n. We will consider actually this expression. This is equal to e to the j 2 pi k n by n times e to the j 2 pi k n by n, which is just equal to e to the j 2 pi k n by n plus, so not plus, times e to the j 2 pi k, which is always equal to 1. Hence, e to the j 2 pi k by n times n is periodic with period n for all k, for any integer k. Since we said for any integer k, it would seem that since k can take all values from minus infinity to infinity, we have an infinite number of different periodic, discrete, complex exponentials which make the grade, which are periodic with period n. Now, while we have an infinite number of them in one manner of speaking, they all of them do not turn out to be different from each other, and this is what we will now show by manipulating the variable k and see what happens if I choose k equal to 0, k equal to 1 and so on. So, for different values of k, for different values of small k. We get e to the j 2 pi into 0 by n just gives you 0, e to the j 0 n. This is the first sequence. Next you have e to the j 2 pi by n into k equal to 1, that is e to the j 2 pi by n into n. Next you will get e to the j k equals 2. So, you get 4 pi by n into n, and going on as thus you will get e to the j 2 pi n minus 1 by n into n. So, how many have we got over here? We started with k equal to 0, then took k equal to 1 and so on up to k equal to n minus 1. So, there are n minus 1 plus of course, the 0 thing. So, we have totally n different functions. Now, suppose we proceed further and write the next function in this sequence. Now, k is not n minus 1, it has reached n minus 1, it is going to become n. So, you will get e to the j 2 pi n by n times n, but this is simply equal to e to the j 2 pi n, which is equal to e to the j e to the j 0 n, because e to the j 2 pi n is the same as e to the j 0 n. That means, after the first n different functions that we got as listed over here, the next member is the same as the first member. There is no difference between the n plus 1th member and the first member. Thus, we find that we have only n different members. You can go further and consider the n plus 1th member, n plus 2nd member, and that will turn out to be the same as the second member. For example, if you consider e to the j 2 pi n plus 1 by n into n, this is nothing but e to the j 2 pi by n into n times e to the j 2 pi n by n into n, which is just equal to e to the j 2 pi n by n. So, all these start repeating as you move further to the right. In short, we have found only n different discrete complex exponentials with period capital N. Though k can be given any value you like and you will end up with a complex exponential, it is just a repetition of an earlier found complex exponential. Now, let us move towards the left and see what happens. We have been going only towards increasing k. The first value we had was k equal to 0. Let us take k equal to minus 1. What is this equal to? It is equal to e to the j minus 2 pi, just a second, minus 2 pi n by n, which is equal to 1. If you go further, you will get e to the j minus 4 pi n by n, which is sorry, this is not equal to n, equal to minus 2 pi, ready, which is nothing but e to the j 2 pi n minus 1 n by n. If you go further to the left and examine e to the j 2 pi minus 2 n by n, this turns out to be equal to e to the j 2 pi n minus 2 by n minus 2 n by n. So, even towards the left, the sequences, the sequence of different discrete periodic complex exponentials repeats. Now, suppose we denote by phi k of n to make our life a little less cumbersome this expression e to the j 2 pi k by n into n. Okay. Suppose we write this, then we have now found that we have phi 0 n, phi 1 n, phi n minus 1 n as n distinct periodic complex exponentials with period n. So, n distinct ones. After this, we find that phi n equals phi 0, phi n plus 1 equals phi 1 and so on towards the right, and towards the left we find phi minus 1 equals phi n minus 1 and so on towards the left. So, in neither direction do you find any new periodic complex exponential. You therefore find for period n exactly n distinct complex exponentials only. Conclusion. We have only n distinct periodic complex discrete exponentials. No more, no less, with which to represent the periodic signal x n equals x n minus n. This is all we have, no more than this. Okay. That means that when we write a synthesis equation similar to what we wrote for x t, we can be very compact about it. It will be a sum only of a finite number of terms. So, we will write the synthesis equation, the tentative synthesis equation x n equals summation x k, which are the weights with which we should add the complex exponential components, phi k n phi k n as k goes from 0 to n minus 1. This seems so much more comfortable than dealing with summing an infinite sequence of components. We just have a finite number of components that have to be added to represent x n. That is all we have. So, with this finite set of components, there are some nice things which happen. There are times when we do not know if the transform representation or the signal representation we have for x n will actually converge to x n. Here there is no such issue, because we are just adding a finite number of terms, and the sum will also therefore be finite because each term is finite. So, this is the synthesis equation. The synthesis equation has dealt in terms of these phi k's of n, each phi k of n being e to the j 2 pi k by n into n. Okay. Now, how do we find the weights x k? To find the weights x k, we hardly need to repeat that we do it in exactly the same way as we handled the problem in the continuous time Fourier series case. We do it by correlating x n with the corresponding complex exponential. So, x k turns out to be equal to 1 by n times summation. This again is a finite summation, n equals 0 to n minus 1 x n e to the minus j 2 pi k by n into n. Fine. Now, this gives the analysis. We have a minus sign in the exponent of the complex exponential here, simply because we have to take the conjugate of the function when one is carrying out a correlation. Now, taking the synthesis and the analysis equations side by side as we have found and rewriting them in this form, the synthesis equation can be rewritten as, for example, one by n summation n equals 0 to n minus 1 x n phi star k of n. This would be the analysis equation. Since both the analysis and the synthesis consist of finite sums, and since they both carry out sums over the same set of basis terms phi k of n, we can now write this in the form of a matrix operation. The whole business of finding the x k's, unlike in the case of the continuous time analysis, turns out to be simply a matter of solving n simultaneous linear equations in n unknowns. N simultaneous linear equations in n unknowns. Fine. With the further assurance, knowing that the equations are independent. Why they are independent, I will come to in a moment. It is because these exponentials that we have are all orthogonal to one another. they are all orthogonal to one another, which is very easy to demonstrate. You just take, say, for example, a summation over one period n equal to 0 to n minus 1 of phi k n and phi star L n, where k is not equal to L. This will be equal to n equal to 0 to n minus 1 of e to the j 2 pi k minus L n by n. Now, this is a zero average signal. Both its real and imaginary parts are zero average. Real and the imaginary component sequences of phi k n phi star L n, both the real and imaginary parts are zero average. Of course, when k and L are different, and hence summing over one period will yield 0. Summing over one period will yield 0. This, however, will not happen when k equals L. K equals L, you will get the summation evaluates to capital N. That is what happens. This is why we say or let us say this is this indicates that phi k n and phi L n are orthogonal for L not equal to k. Orthogonality, it turns out, is a repeated theme in our study of various kinds of representations. For the Fourier series, we have already shown that the Fourier the complex exponentials e to the j omega naught t and e to the j 2 omega naught t, for example, or in general e to the j k omega naught t and e to the j L omega naught t were always orthogonal. So, let us just have a small digression about the orthogonality of these representing functions. In the continuous time Fourier series, we have e to the j 2 pi by t k t is orthogonal to e to the j 2 pi by t L t for k not equal to L. Orthogonal is orthogonal to that means that over one period 0 to t e to the j 2 pi k minus L by t of t equals 0 for k not equal to L. This is what we have. This is the proof of orthogonality for the CTFS. For the CTFT, we have similarly again that the integral, the inner product, this time evaluated again over one period, but now the period is infinity from t equals minus infinity to infinity, still yields 0. That is, if you have an integral from minus infinity to infinity of e to the j omega t multiplied by e to the minus j omega dash t dt, which is the same as saying integral minus infinity to infinity e to the e to the j omega minus omega dash t ready to go. Now, even if omega and omega dash differ by a very small value, differ by an extremely small value, still e to the j omega minus omega dash t is a periodic complex exponential with 0 average, real and imaginary parts, when the averaging is carried out over a large interval. Such as minus infinity to infinity. Thus, any two exponentials used, any two distinct exponentials used in the CTFT representation are always orthogonal. So, that is true, as it turns out, as much for the CTFT as it was for the continuous time Fourier series. And again we see a manifestation of the same thing when we dealt with the discrete time Fourier series. We have only n different complex exponentials there, which have all the period of capital N, and each of them is orthogonal to every one of the other members of the set. And it is because these different exponentials are orthogonal with respect to each other that we get a set of independent linear equations, and because they are independent, what we get is a matrix equation to solve where the matrix has full rank. We are now going to write the equation in matrix form. The take so now let us make a matrix of all the equations that go into determining the analysis. So, for the analysis we have the analysis equation x k equals 1 by n summation n equals 0 to n minus 1 x n phi k n star. This is what we have. This written out in plain language will give you a matrix of this form, a matrix equation of this form. You have x k, which is x 0 going on to x n minus 1 equals the matrix phi 0 0 phi 0 1 on to phi 0 n minus 1. Next row is phi 1 0 phi 1 1 going on to phi 1 n minus 1, and finally phi n minus 1 0 phi n minus 1 1 phi n minus 1 n minus 1. All of them of course conjugated, something I forgot. So, you can put star 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 this thing times x 0 to x n minus 1. This is the analysis equation. Now, for synthesis, we have the equation x n equals summation k equals 0 to n minus 1 x k e to the I will just write it in terms of our abbreviated notation, and write x k phi k n. So, now we do a summation over k's instead of n's, and thus we have the synthesis equation in matrix form as x 0 to x n minus 1 equals phi 0 0 phi 1 0 so on to phi n minus 1 0 phi 1 0 phi 0 phi 0 of 1 phi 0 of 1. So, phi 0 of 1 was the first term in the second row, then phi 1 of 1 going on to phi n minus 1 of 1 and so on until you finally have phi 0 of n minus 1, phi 1 of n minus 1 going on to phi n minus 1 of n minus 1 times x 0 to x n minus 1. The coefficients x 0, x n minus 1 are called the discrete time Fourier series coefficients. Coefficients. Now, it is important to ask whether we have only 8 whether we have only n different discrete time Fourier series coefficients or there are more. The answer is that there are only n, because these Fourier series coefficients are found as correlations of the corresponding complex exponential, discrete complex exponential with the original function. Since there are only n different discrete complex exponentials, periodic complex exponentials, which can be correlated with x n, we will get only n different discrete DTFS coefficients. So, we have the DTFS coefficients satisfying a periodicity property. You have x 0 going on to x n minus 1. Then if you write x n, it turns out to be equal to x 0, x n plus 1 will be equal to x 1 and so on this side. And if you go towards the left and write x minus 1, that will turn out to be equal to x n minus 1. If you write x minus 2, that will turn out to be equal to x n minus 2 and so on towards the left side. So, in short, you only have these many really distinct coefficients, no more than these. And the periodicity that you observe is a very, very important property of the discrete time Fourier series coefficients. You do not have an unlimited number of coefficients like was the case with the continuous time Fourier series, but only a finite n number of different coefficients.